Welcome grade 7 students. So, how are you? Are you good? Okay, so please go to www.cathopeschool.com. Okay, then enter for the curriculum and enter the password. Alright, then click for mathematics because that will be our subject for today, mathematics. Okay, math. So, um, are you ready? Okay. So first, our lesson will be rational numbers. That will be our lesson for today, rational numbers. So before we will know the terms and definition of rational numbers, I have this video here for further understanding or a little introduction for you about rational numbers.
All of us know what a number line is. And all of us know what a number line is. And the numbers we see here on the number line are called integers. On the right side of 0, we have positive integers, and on its left, we have negative integers. Integers we are familiar with, but what about numbers like these? 1 by 3, 5 by 6, or minus 7 by 12. Each of these are numbers, but we don't use them as often as we use counting numbers. Such numbers are called rational numbers, but we need to define them well. We cannot say numbers like these are rational numbers. We say that they are of the form p by q, one number in the numerator and one in the denominator. But there are a few conditions we need to know. P and q should be integers. We can have only integers in place of p and q. And there is another important condition. Q should not be equal to 0. Why do we have the second condition? Say I ask you to calculate 3 divided by 0. What would be the quotient? 0 multiplied by what will give you 3? There is no such number. This value is undefined. So this is the basic definition of rational numbers. It is a number of the form p by q, where p and q are integers, and q is not equal to 0. There are many questions that should pop up in your head when you see this definition. What is the difference between rational numbers and fractions? Are integers classified as rational numbers? What about 0? How do we plot such numbers on a number line? And how do we compare two rational numbers? For example, if you are asked to compare 1 and 5, you could easily say that 5 is greater of the 2. But what if you're asked to compare numbers like 6 by 7 and 13 by 15? How would you find out which one is greater? Don't worry about it. All these questions will be answered in our videos on rational numbers.
Okay, so wait a minute. So rational number is any number that can be expressed as a ratio of two integers. It can be written as a fraction in which the top number is divided by the bottom number. So all integers explained in the video are rational numbers since they can be divided by 1, which produces a ratio of two integers. So many floating point numbers are also rational numbers since they can be expressed as a fraction. For example, 1.5 is rational since it can be written as 3 over 2 or 6 over 4 or 9 over 6 or another fraction or two integers. Pi is irrational since it cannot be written as a fraction. A floating number is rational if it meets one of the following criteria. Number 1, it has a limited number of digits after the decimal point. Example, 5.4321. Number 2, it has an infinitely repeating number after the decimal point. Example, 2.333333. Number 3, it has an infinitely repeating pattern of numbers after the decimal point. Example, 3.151515. If the numbers after the decimal point repeats definitely with no patterns, the number is not rational or irrational. Below are example of numbers of rational and irrational numbers. So 1 is rational, 0.5 rational, 2.0 irrational, 2.0 rational, square root of 2 irrational, 3.14 rational, pi is equal to 3.1415926, and so on, irrational, pi square root of 4 rational, square root of 5 irrational, 16 over 9 rational, and 1 million point 0001 is irrational. In the computer science, it is significant if a number is rational or irrational. A rational number can be stored as an exact numeric value, while an irrational number must be estimated. So, I also have this video so that you can furthermore understand what is rational or irrational number. Okay, wait a minute.
As 15 over 4, or we could write this as negative 30 over negative 8. I just multiplied. So let's talk a little bit about rational numbers. Rational numbers. And the simple way to think about it is any number that can be represented as the ratio of two integers is a rational number. So, for example, any integer is a rational number. 1 can be represented as 1 over 1, or as negative 2 over negative 2, or as 10,000 over 10,000. In all of these cases, these are all different representations of the number 1, ratio of two integers. And I obviously can have an infinite number of representations of 1 in this way, the same number over the same number. The number negative 7 could be represented as negative 7 over 1, or 7 over negative 1, or negative 14 over positive 2, and I could go on and on and on and on. So negative 7 is definitely a rational number. It can be represented as the ratio of two integers. But what about things that are not integers? For example, let us imagine, let's imagine 3.75. How can we represent that as the ratio of two integers? Well, 3.75, you could rewrite that as 375 over 100, which is the same thing as 750 over 200. Or you could say 3.75 is the same thing as 3 3/4, So right here, 3 3/4, which is the same thing as, that's 15 over 4. 4 times 3 is 12, plus 3 is 15. So you could write this. This is the same thing as 15 over 4. Or we could write this as negative 30 over negative 8. I just multiplied the numerator and denominator here by negative 2. But just to be clear, this is clearly rational. I'm giving you multiple examples of how this can be represented as the ratio of two integers. Now what about repeating decimals? Well, let's take maybe the most famous of the repeating decimals. Let's say you have 0.333, just keeps going on and on forever, which we can denote by putting that little bar on top of the 3. This is 0.3 repeating. And we've seen, and later we'll show that how you can convert any repeating decimal into a rational as the ratio of two integers. This is clearly 1 over 3, or maybe you've seen things like 0.6 repeating, which is 2 over 3. And there's many, many, many other examples of this. And we'll see any repeating decimal, not just one digit repeating, even if it has a million digits repeating, as long as the pattern starts to repeat itself over and over and over again, you can always represent that as the ratio of two integers. So I know what you're probably thinking. Hey Sal, you've just included a lot. You've included all of the integers. You've included all of non-repeating decimals, or you've included all of finite non-repeating decimals, and you've also included repeating decimals. What is left? Are there any numbers that are not rational? And you're probably guessing that there are, otherwise people wouldn't have taken the trouble of trying to label these as rational. And it turns out, as you can imagine, that actually some of the most famous numbers in all of mathematics are not rational. And we call these numbers irrational. Irrational. Irrational numbers. Irrational numbers. Irrational numbers. And I've listed just a few of the most noteworthy examples. Pi, the ratio of the circumference to the diameter of a circle, is an irrational number. It never terminates. It goes on and forever, and it never repeats. E, same thing, never terminates, never repeats. It comes out of continuously compounding interest. It comes out of complex analysis. E shows up all over the place. Square root of 2, irrational number. Phi, the golden ratio, irrational number. So these things that really just pop out of nature, many of these numbers are irrational. Now you might say, okay, aren't these irrational? These are just kind of these special kind of numbers. But maybe most numbers are rational, and Sal's just picked out some special cases here. But the important thing to realize is they do seem exotic, and they are exotic in certain ways, but they aren't uncommon. It actually turns out that there is always an irrational number between any two rational numbers. And that, well, we could go on and on. There's actually an infinite number. But there's at least one. So that gives you an idea that you can't really say that there are fewer irrational numbers than rational numbers. In the future video, we'll prove that you give me two rational numbers, rational 1, rational 2, rational 2. There's going to be at least one irrational number between those, which is a kind of a neat result because irrational numbers seem to be kind of exotic. Another way to think about it, I took square root of 2, but you take the square root of any non-perfect square, you're going to end up with an irrational number. You take the sum of an irrational and a rational number, and we'll see this later on. We'll prove it to ourselves. The sum of an irrational and a rational is going to be irrational. The product of an irrational and a rational is going to be irrational. So there's a lot of irrational numbers out there.
Okay. So okay, I hope you understand the difference of rational and irrational, because we'll go to the ordering of rational numbers. I'll show you the video of what is or how to order rational numbers.
Number line. Let's just take them. What I'd like to do in this video is order these 6 numbers from least to greatest. So the least of them being on the left-hand side and the greatest on the right. And I encourage you to pause this video and see if you can do it on your own before we work through it together. So assuming you've had a go at it, so let's do it together. And to help us there, let's plot these numbers on a number line. Number line appears. There you go. There is a handy number line. And let's just take them one by one. So the first number here, we have 7/3. So let's see if we can express that in a different way. We can write that as a mixed number. So 7/3. How many wholes are here? The whole is going to be 3/3. So this is going to be, let's see, this is going to be 3/3 plus another 3/3. It's going to get us to 6/3. So you're going to have one more third left. So this is 7/3. 3 plus 3 plus 1 is 7. So this is 3/3 is 1 whole. 3/3 is 1 whole. So this is 2 and 1/3. So 7/3, same thing as 1, 2, and you see between consecutive integers we have 3 spaces. So we are essentially marking off thirds. So 2 and 1/3 is going to be 1/3 of the way between 2 and 3, so it's going to be right over there. So that is 7/3. Then we have -5/2. So same logic, negative 5 over 2 negative of 5 halves, and 5 halves is going to be 2 halves plus another 2 halves plus 1 half. So this is 2 and a half. This is 1, and that's a half. This is going to be 1 plus 1 plus 1 half, 2 and a half. And we're negative out there, so it's negative 2 and 1 half. Let's see, negative 1, negative 2, and then negative 2 and a half is going to be halfway between negative 2 and negative 3. It's going to be right over there. So that is negative 5 over 2. Then we have 0, not too difficult. It's actually labeled on our number line for us. Then we have negative 2. Negative 2, once again, on our number line for us. Two steps, 2 whole numbers to the left of 0. Negative 2 is going to put us right over there. Then we have negative 12 fourths. So it might jump out at you immediately. 12 divided by 4 is 3, so it's going to be the same thing as negative 3. This is negative 12 fourths, or if you want to use the type of logic that we used in these first two numbers, you can say negative 12 over 4 is the same thing as the negative of 12 fourths, which is 4 fourths plus another 4 fourths, so that gets us to 8 fourths, plus another 4 fourths. That's 12 fourths. This is 1, 2, and 3, or negative 3. So negative 3 is the same thing as negative 12 fourths. And then finally, one more number, negative 3.25. So you could view this is the same thing. Negative 3.25 is the same thing as negative 3 and 25 hundredths. And 25 hundredths is the same thing as 1/4. 25 is 1/4 of 100. So this is the same thing as negative 3 and 1/4. So let's see, let's go negative 1, negative 2, negative 3. Then we have to go a fourth. And we're not going to be able to do it super precisely, but it's going to be less than a third. So it's going to be right over there. So that right over there is negative 3.25. So we wanted the numbers ordered from least to greatest. Well, we've done that. The least is negative 3.25, then negative 12 fourths, then negative 5 halves, then negative 2, then 0, then 7 thirds. And we are done.
Okay. So, another video that is shown about we all have I also have this classifying numbers
Which
of
the
rational
following
and
real numbers
irrational.
are irrational? Well, irrational just means it's not rational. It means that you cannot express it as the ratio of two integers. So let's see what we have here. So we have the square root of 8 over 2. So square root of 8, if you take the square root of a number that is not a perfect square, it is going to be irrational. And then if you just take that irrational number and you multiply it and you divide it by any other numbers, you're still going to get an irrational number. So square root of 8 is irrational. You divide that by 2, it is still irrational. So this is not rational, or another way of saying it, it is irrational. Now you have pi, 3.14159, it just keeps going on and on and on forever without ever repeating. So this is irrational, probably the most famous of all of the irrational numbers. 5.0, well I can represent 5.0 as 5 over 1. So 5.0 is rational, it is not irrational. 0.325, well this is the same thing as 325 over 1,000, so I can clearly represent it as a ratio of integers. So this is rational, just as I could represent 5.0 as 5 over 1. Both of these are rational, they are not irrational. Here I have 7.777777, and it just keeps going on and on and on forever. And the way we denote that, you could just say these dots that say that the 7s keep going, or you could say 7.7, and this line shows that the 7 part, the second 7, just keeps repeating on forever. Now, if you have a repeating decimal, in other videos we'll actually convert them into fractions, but a repeating decimal can be represented as a ratio of two integers, just as 1/3 is equal to 0.333, on and on and on, or I can say like this, I can say 3 repeating. We can also do the same thing for that. I won't do it here, but this is rational, so it's not irrational. 8 1/2, well that's the same thing. 8 1/2 is the same thing as 17 halves, so it's clearly rational. So the only two irrational numbers are the first two right over here.
Okay. This will be the end of our discussion, but we will continue because on our next video I have practices, so please study our lesson for today because on our next video we will continue. I'll give you some practices on how to identify irrational and rational, and of course the ordering and comparing of rational numbers. Okay, thank you.